Hi, this is Mr. T here. Welcome to a series of 3 videos answering 2016 Level 3 Physics Demonstrate Understanding of Mechanical Systems. So I'm going to go through show you how I answered this and how I approached this. And we'll go through and see how to get an excellence in this paper. Okay, so one thing to notice about this paper, if you're going to be sitting at 2017, it's worth 6 credits, and you're going to spend about an hour 10, maybe an hour 15, completing it during your exam. Okay, so in this video, I'm going to go over the first question. The first question here is about circular motion. So let's get into it. Now, what we know about circular motion is that we have two forces, we have forces that will produce a centripetal force. In this case, it's a banked curve. Okay, so the car here is going around in a circle. It's a roller coaster car. So the two forces that are acting on it, in this case is gravity and support force, must be adding together to produce a centripetal force to make it turn. Now, the first thing they ask us to do here is, on the diagram above, draw labeled diagrams. So that's cool. We know that this is going to be, that is not the best one in the world, but that'll do. So that's my support force, and then I'm going to draw, let's do that again. And then I'm going to draw a gravity force. Yep. So this is a force of support, and this is a force of gravity. Make sure you do these in the proportion to each other, because the height of the support force here should be the same as the height of the gravity force, and the support force should be perpendicular to the surface, and the gravity force should be going directly down compared to the actual to the ground. Okay. So no friction, I don't have to draw that. So this is a force on our diagram here. So this is we're going to now put this into a triangle so we can calculate the centripetal force. We're going to have to use trigonometry. Now, trigonometry, we're going to use SO, car, or toa, right? So let's draw our triangle here. So we had going directly down, force of gravity, and we had a support force. There it is, in that direction, and then we had a force that was the resultant force, and this is the centripetal force, and of course it's going to go to the left because our car is going to be turning around to the left as we view it there. Well, that's if these, if they're going backwards into the page. Okay, so what information have they given us? They've given us the M, and they've given us the theta. Now, in this case, theta is this acute angle, 20 degrees. Okay, I'm not going to go through the geometry of this, but usually it's pretty straightforward. You can see that the sharp angle is 20 degrees, so when we draw a triangle, same as. Okay, now we don't know. So let me do the support force better. We don't know the support force. We don't know the centripetal force or the gravity, but we can work out the gravity force because we know that Fg equals m times g. And they've given us a mass, 9.6 times 10 to negative 2, which is 960. Oh, sorry, not to negative 2, to the 2 kilograms, times 9.81. Meters second negative 2. Okay, so we get Fg equals to 9417.6 newtons. So that's Fg. So now we know one of the sides, and we know an angle, so we can go ahead and do a trigonometry calculation. I want to find Fc. In this case, it is the opposite to our angle, and Fg is the adjacent. So we're going to use TOA, or tan. So we remember that tan theta equals opposite over adjacent, or opposite equals tan theta times adjacent. Okay, so I just moved what was on the adjacent that was at the bottom on the right hand side, I moved it over to the left hand side and it came onto the top of our expression. So now we substitute in the values. So opposite is FC. We have tan theta is 20 degrees. And we have multiplied by the adjacent, which is the force of gravity, of course, which is 9417.6. And we get an answer to this. Now, our answer to this is 3,430 if I round it to 3 significant figures, which I will do in this case because, well, if I disregard the 20 degrees, so I've got 3 significant figures here, and I have 3 significant figures from my gravity value as well. Sorry, my acceleration due to gravity. Okay, so that's question 2. So now we're looking at the cart as it goes around the circle. Okay, so it's going around a vertical circle. So we've got it in 2 different positions here, position A and position B. Now this question C asks us, compare the force of the track exerts on the car when the car is at the top of the hill, position A, with the force the track exerts on the car when it's at the bottom of the hill. That's position B. So let's look at position A for a start. Well, actually, let's look at both of them. They both have a gravity force acting on them. And the mass of this vehicle doesn't change, so the gravity force is the same at both places. Now, at this position A, the car is not accelerating up or down, so the force of support equals the force of gravity. So let's write that down. So at position A, the forces are balanced. You can say the net force equals 0 as it is not accelerating. It is not accelerating. You could say the car is not accelerating. So Fs equals Fg. Okay, that's pretty cool. Let's go have a look at B. Now B's a wee bit different because what we see with B here is it's actually beginning to move around in a circle. Okay, so it's starting to turn. So what we actually have here is we have a centripetal force. It needs that to turn. Now, in order to provide a centripetal force, you have to provide a support force that is large enough to cancel out all of the gravity and then produce a centripetal force. So we're going to get a support force like this. So you can imagine if I drew the gravity here, here's my Fg, and here's my Fs. I add those together, Fs, then my centripetal force is the resulting vector. Yep. So here all that we need to say is that at B, the support force needs to be larger larger than the Fg in order to produce the centripetal force needed to make the cart turn. Cool. Let's go on to the next bit, D. Okay, so D is top of the track, circular loop. The force of the track. Oh, okay. Let's just draw this. So because we had a track that was up there, it kind of looked like that. They tell us here that the height, that is the height. They've told us the radius here equals 5.00 meters. Okay, and we know at the top here, top of the circular loop, the force that the track exerts on the car is 0. Now, what actually happens, and we said this before, is the centripetal force is equal to the force of the support plus the force of gravity. Now, of course, these are vectors, so you don't add that. You have to take into account the direction they're going. But at the top of the loop, there's no support force, then Fc equals Fg. So this is quite important, because what we're going to do is we're going to take this equation here, the centripetal force equation, and that equals mv squared over r, and we're going to substitute our gravity equation, and the gravity equation, Fg equals mg. So we're going to put mg, because Fc equals Fg, then Fg, and Fg equals mg, we can put mg in here. Mg equals mv squared over r, and we can simplify by cancelling out the two m's, and I want to rearrange this to find the velocity at the top. Okay, so we get v squared equals g times r, or v equals the square root of g times r, equals the square root of 9.81 times 5. And that gives us an answer of 7 meters per second. So that's all fine and good. Why did I do that, you ask? Well, look, at the top of this loop, the total amount of energy we have must equal the energy at the top. And if I know the potential energy at the top, because I know the gravity and I know the mass, I can work out the height. So what I know at the top part here is I have potential energy and I have kinetic energy. Now, because I have this velocity, I can work out the total amount of kinetic energy. That equals half mv squared. M is 960 times 7.00 squared. Okay, and that's going to give us an answer of not quite sure at the moment, but just let's leave it as that. Let's do that. Potential energy at the top equals mgh. So again, m is 960 kilograms times 9.81, that's g, times h. So the height here from the bottom is 2 radiuses, 1 diameter, 10 meters. Yep. So the total energy, the EP total, right, equals the kinetic energy, half 960 times 7.00 squared plus 9.60 times 9.81 times 10. This total potential energy, this is all of the energy that it has, or the energy at the start, is equal to 107,696 joules. Okay, so if I know the total potential energy, then potential energy equals mgh. So H equals EP divided by mg. H equals 117,696 divided by the mass, which was 960 kilograms, and also divided by the 9.81. Now when I carry out this calculation, I make sure I do the bit at the bottom in brackets, and the answer I get is 12.5 meters. So the height above for this car is 12.5 meters. Does that seem approximate? Or does that seem right? Well, let's have a look. Let's go back to our diagram. So the height here is, okay, to here it's 10 meters, and what we're saying, it's about another 2.5 up there. So that seems reasonable, and we're quite happy with that. So yeah, that's it. This is the first question answered for this 2016 mechanics paper. Thanks for listening.